AP Chemistry. This is the answers video for Day 52 Integrated Rate Law. It's November, signed November the 12th, Thursday, and due on Monday, November the 16th. Alright, so let's go ahead and do this. We're going to start off with basic question. We just want to always be sure we know what we're doing and why we're doing it. What is kinetics? That's the subject we're dealing with. It's simply the study of the rate of a chemical reaction, how fast a chemical reaction takes place. Now, there's two ways you can study the rate. One is at a very specific moment in time. How fast is it going at a very specific moment in time when you have certain concentrations of the reactants? And that's kind of like looking, the analogy I used in the video is looking at the speedometer of a car. The speedometer, if the speedometer of a car says 60 miles per hour, it means you're going 60 miles per hour at exactly the moment you looked at the speedometer. It's not 5 seconds before or 5 seconds later or for the entire duration of the trip that you're on. It's just at the exact moment you're looking at it, that's the speed that you're going. That's called an instantaneous velocity. So we first developed a rate law in the last lesson for an instantaneous rate, the rate at a very specific moment in time given certain concentrations. What we're going to get into in this case is the average rate, or the rate between 2 points in the reaction, so a beginning point and an ending point. So you have a change in the concentration and you have a change in the time. That's kind of like the speed that you would have if you drove from San Diego to Los Angeles, and that's 120 miles and it takes you 2 hours, so you're going 60 miles per hour. That's an average velocity. And that's what the integrated rate law is going to deal with, the average speed between two different points in the reaction. So what we're going to do is start off with one of the problems similar to the last lesson. That's an instantaneous rate. And we're going to use the rate law for that. So we're going to work another one of those problems. So here it is. And by the way, I want to make it clear where you are. You are more than halfway into a college chemistry book with these problems. I got this from one of the reference texts I use. It's chapter 14, problem number 45. So you are well into a college chemistry book. What I want you to just do is, accept this challenge. It's a challenging class. Struggle to understand it. I don't expect you to understand everything, but understand as much as you can. This is really just your first time through this material. The second, third, and fourth times will come in the spring, maybe over some of the breaks that we have coming up. But if you want to pass that test, it's going to take a real effort on your part. So I hope that's something you value, and because that's the only way. You just have to have the desire to pass the AP exam in chemistry. If you do, I think you'll view it as one of the great accomplishments that you'll have in high school, because it's a very challenging test. Okay, so let's go ahead and do this problem. It's like a couple that you had in the previous assignment. So it says that you were given these data for this reaction, and what it's saying is that you had a concentration of 0.1, and you did 4 reactions, and we're going to just number them. 1, 2, 3, 4. So you ran this 4 times with 4 different concentrations. 0.1 of NO2 and 0.1 of F2, and when you ran the reaction with those concentrations at exactly a specific moment in time, the rate was 0.026 molar per second. For reaction 2, you had these 2 concentrations, and that was the rate. You had these 2 concentrations in reaction number 3, and that was the rate, and for number 4, it's these 2, that's the rate. So what you do is you pick these 2 at a time. And so what you have to know in order to derive an equation from data points like this, you have to know the form of the equation. So the form of the equation is this. Okay, there you go. That's the form of the equation. So the rate is going to equal some rate constant, which is a function of 3 things. The temperature. Higher temperature usually means higher rate law. The reaction will go faster. Activation energy. The lower the activation energy, the amount of energy it takes to get the reaction going, then the higher K is, the faster the reaction will run. And something called the frequency factor. It's how frequently the particles smash into each other, break apart. So those are all embodied in this variable K, or it's actually a constant K. Then you have the concentration of A raised to some power, and the concentration of B raised to some power. So what we're trying to do is fill out everything on this side, and that will allow us, we can leave A and B as variables. In other words, we can insert different concentrations of A and B, and that will tell us what the rate will be given those two concentrations. So the first thing we can do for this problem is we can go ahead and start filling in those concentrations for this specific reaction. Okay, so there it is. That's a Y up there. It doesn't look so good, but that's a Y. Okay, that's just like that. Okay, so we know the reactants we're dealing with. Now, it doesn't have to always be 2. It could just be a single reactant. It could be 3 reactants. In this case, it happens to be 2 reactants. Okay, so we've done that. So let's look at the questions we're being asked. What is the order of the reactants NO2 and F2? And what is the order of the reaction? So those questions we're going to have to wait till the end. The first thing we need to do is come up with the parameters of this equation. And that's what this question is asking you to do. Write the complete rate law for the reaction. It's actually not a question, it's just an instruction. Write the complete rate law for that reaction. Okay, so the way we do this is we want to see what effect that NO2, the concentration of NO2, has on the rate. So what we want to do is we want to find 2 reactions where NO2 changes. But we want to hold F2 constant. You don't want both of them changing, otherwise you can't isolate the effect of NO2. So you want to keep F2 constant and find 2 reactions where F2 stays constant and NO2 changes. And if you look here, you can see that numbers 1 and 2 would do that. F2 stays at 0.1, it doesn't change, and NO2, we have a difference in NO2s at 0.1 in one of the reactions and 0.2 in the other. So that means what we're going to do is compare these concentrations with these rates in reactions 1 and 2. So I'm going to come over here and we're going to do that calculation. So NO2 first is what we're doing. And we chose reaction, RxN is reactions 1 and 2 to study. Now what you're going to do is create a ratio of these 2 numbers and compare it to the ratio of these 2 numbers. It doesn't matter which ones you put on top, you just have to be consistent. So what you usually choose is come over here to the concentration. You put the bigger number on top so you can avoid having a fraction if possible. So what we're going to do is we're going to take reaction 2 and put it over reaction 1. Okay? So reaction 2 says that the concentration for NO2 is 0.200. And for reaction 1, there it is, that. So if you take that ratio, it simply gives you 2. 2 to 1 ratio. So what you did is you doubled the concentration of NO. Now we're going to see how that affects the rate. So again, we're going to take, so this is concentration. I'm going to just squeeze it in there, concentration. And now we're going to do rate. And we're going to do the same thing, reaction 2 over reaction 1. You have to do it in the same one on top. So reaction 2 over reaction 1. You can't flip it here. Okay, and we come over here, and that's 0.051. Okay, and if you do the math on that, you don't get exactly 2, but it's pretty close to 2. Close enough that we can call it 2. Okay, now the next step is, be careful, you got to be sure you do this in the right order here. You are going to find out what this exponent, we're trying to find out what this exponent x is. And we see that when you double, when you double the concentration of NO, what it did was cause the reaction to be twice as fast. Now you may remember from the video what that means, what kind of reaction that is, but if you don't, that's okay. Don't expect you to. So we take this one, the ratio that comes from the concentrations, that's these 2 over here, and we put it right there. And then we take this one, the ratio that you get from the rates, that's these 2 right here, and you put it here on the other side of an equal sign. And then you simply raise this to the x power. Okay, so you simply have to answer the question, 2 to what power gives you 2? This one's pretty obvious, x equals 1. If it wasn't obvious, and there might be some that aren't, but very few in these exercises, You would take logs. You take log of 2 to the x, log of 2, the x comes out front, you got log 2, and they cancel, and you end up with x equals 1, okay? I won't get into detail unless we hit that situation. So what it means is it's a first-order reactant. X is a first-order reactant. That's the definition of a first-order reactant. When you double the concentration, it doubles the rate. That's what a first-order. If you tripled the concentration, it would triple the rate. So on and so forth, okay? All right, so that takes care of that. Now we're going to come here. I'll draw a little line here, and we're going to do the same thing for F2. We're going to figure out what y is. This variable, this thing that doesn't look like a y, that's a y. We're going to figure out what y is, okay? So that's F2. And so we need to find two reactions where NO2 remains constant and F2 changes. So if we come over here, we see that reactions 2 and 3, NO2 stays the same, 0.2, 0.2, and F2 changes. All right, so we're going to pick reactions 2 and 3. And we're going to do what we did before. We want the bigger one of these two on top. So we want 0.2 over 0.1. So we're going to go ahead and do that. So for the concentration, okay, and we end up with the same thing, a 2. All right, now we're going to do the same thing for the rate. Again, we put 3 over 2 because 3 was bigger. This one was bigger than this. Now we're going to do the same thing here. Okay, we're going to put 103 over 0.051. And again, if you do the division there, you get approximately 2. It's close enough to call it 2. All right, so we kind of ended up with the same thing there. It doesn't always work that way. It just happened to in this problem, 2 and 2. So if you double the concentration of F2, you're going to double the rate of the reaction. So we know what kind of reaction that is, but let's go ahead and write it out. So you take this one from the concentration, put the 2 there, take this one from the rate, put the 2 there, put an equal sign, and put the y there. And so in this case, y is going to also equal 1. All right? So we can go ahead right here and start filling this out as we go along. So rate equals K. Now I'm going to write K very lightly because we're going to erase it eventually, times the concentration of NO2. And we just figured out that's raised to the 1 power. You don't have to write that, but again, that's the one that we got right there. Goes there. Just want to emphasize where it goes. And then it's F2, also raised to the 1st power. And that's the one that we got there for Y. That goes there. So now we've gotten everything here. The only thing we need to do is figure out what K is. What's the equilibrium constant? So how do you do that? Well, it's pretty easy. Look what we have. We have F2. We know we can pick. Well, first, we pick a reaction. It doesn't matter which one. You could pick reaction 1, 2, 3, 4. Pick any one you want. I'll go ahead and just go ahead and pick. I'll pick 2. Why not? Could have picked any of the others. Okay, so the concentration of NO is 0.2. We know that number. The concentration of F in reaction 2 is 0.1. We know that number. And for this reaction specifically, the rate is 0.051. We know that number. So the only thing we don't know is K. So what we're going to do is go ahead and plug in those numbers. So you get this. Just note that we picked reaction 2. We could have picked any of the other 3. Okay, and that equals, write it lightly. And I'm going to use parentheses since it's now a math equation here. Okay, so we have 0.2. And we have 0.1. All right, so now it's just a simple algebra problem. You divide both sides by these two. And that means you divide this side by those two as well. Just draw a line here so we're clear there. Okay, and of course this all cancels out, so the only thing you have left on that side of the equal sign is the K. So go ahead and just do the math on that. And you get 2.55. Okay? Okay, therefore the equation is going to be, at the end, I'll go up back to the equation we're filling out here, is going to be 2.55. And I'm actually going to do something else here for a sec. Okay, I'm going to put an equal sign. I'm going to call it 2.6. Okay, I'm going to call this equals 2.6. All right, just round it. So I have 2.6, but 2.6 what? Well, you need to have units of measure for K. One thing with a kinetics problem, depending on the order of the reaction, will determine what the units of measure for K are. That's a question they could ask you on the AP exam. So let's know how to figure that out. By the way, we can now answer these questions. What is the order of reactants NO2 and F2? Okay, so NO2 is first order. That's what the exponent means. F2 is first order. Exponent there. That's the answer to this one. To this one, what is the order of the reaction? You simply add the exponents. Okay, the reaction is second order. Okay, so this is a second order reaction. The units of measure for a second order reaction are different than the units of measure, I should say, for K, for a first order or for a zeroth order. So how do you figure out what they are? And as I say, that's something they could ask you on the AP, so let's know how to do that. What we do is, here's our equation. Recognize that rate is always expressed in molar per second. It's a speed. It's how many moles per liter the reactant is decreasing per second. It's how fast it's decreasing. So rate is always in molar per second, no matter what order the equation is. So it's that. And that's going to equal K. We're trying to figure out what the units of measure for K are. And concentrations are always measured in molarity. Okay, so it's M and it's M. M times M. M times M. Now, there's no exponent because it's to the first order. There really is an exponent, it's to the first. If this had turned out to be a second order reactant, a 2 there, then you would have put a 2 up there. If it had been a third order, which is very rare, you would have put a 3 up there. Okay? So but in this case, they're both first order reactants, so it's MM. So all you do now is you divide both sides by this. Okay? And I'm going to come down here. Those cancel, and come down here, and what you end up with is K equals M over, these M's came down to the bottom here, and you already had that S there, MMS. So this molar cancels with one of these, and what you have here is you have 1 there over MS. So your K is going to equal, we'll just write it out, 2.6, and the units of measure are 1 over molar seconds. Now you may ask, what does that mean, a molar second? It doesn't matter. It's not something you have to deal with. Okay? It's just what the units have to be for K in order for the units to cancel out so that you end up with molar per second for your rate. Your rate has to always be in molar per second. Okay? So there you go. And I was going to try to write the M 1 over MS there, but it's not enough space. So this is really your answer right there. All right? Okay, that's how you do this. All right. Okay, I'm going to do this one on a different piece of paper simply because I didn't leave enough space down here to do this. So you can do it on the back, or you can do it if you're doing it on line paper. Fine, do it on line paper. Okay, so what I'm going to do is copy this reaction to the other side. So I'll go ahead and do that. Okay, so I've copied the problem on the back of the page. Feel free to do the same thing with yours, because there's really not enough space down there. Okay, so you're talking about the rate of appearance of NO2. F2 is consumed at this rate. at what rate is N2OF this produced. Okay, so this is a rate expression problem, one of the ones we did way back at the beginning. So write this entire equation as a rate expression. See if you remember how to do that. Okay, you can stop the video and try it, and I'll go ahead and do it. Okay, so here we go. So what you do is you take the reciprocal of the coefficient, and since it's a reactant, a negative sign goes in front. Does that bring it back to you if you didn't remember that? And then it's going to be times delta NO2 over delta T. Remember, there's an implied negative sign in here because it's a reactant. You know it's decreasing, so negative is going to make the rate positive. Rates must be positive. Okay. Over here you have F2, so it's negative. I'm going to put plus a negative, and it's delta F2, and I really should put this in concentration signs here, and it's also over delta T. Delta T, whatever number that is per second per minute, it's the same. It means these two things have to be happening at the same time, okay, in the same amount of time. You're doing whatever these are doing. Okay, and now we have I'm sorry, that shouldn't be a plus. How many of you caught that? We're writing a rate expression that equates the rates. So that's an equal sign. Okay, and now we're going to equate that to the rate at which the NO2F is being produced. And since it's being produced, it's increasing, that's a positive. So that's going to be, I'll just put a little plus to symbolize that. It's 1 over 2, 1 over its coefficient. And there's no implied negative sign here because it is increasing, it's not negative. Okay, so there's the rate expression for that equation. So the only one we're interested in is F2. F2 is consumed at this rate, so we're interested in this. And at this rate, and we're interested in the production of this. So we're simply going to plug in the number. Okay. All right, so this is consumed at this rate, so that is going to be and rates are always positive, so it's going to be 2.2 times 10 to the negative 1. I'm not going to put the units of measure here because they're both the same. And that equals 1/2 of all of this. And I'll put this in a big parenthesis. Okay? So all you're doing is solving for this. So that's an easy algebra problem. You multiply both sides by 2. 2 over here. Cancels with that 2. And now you have isolated the variable you're trying to find. So 2 times 2.2 is going to be 4.4 times 10 to the negative 1. And it is a rate. So it's molar per second. Okay, and it makes sense. You're getting, if you go back to the original equation, you're getting 2 moles of this for every 1 mole of this that you use up. So for every 1 molar of this you use, you're getting 2 molar of this. So this number is going to be twice what that number is. So this number was 2.2, so this number is going to be 4.4. So that one's kind of easy, almost one you could do in your head, but not all of them are. So that's the way you do a rate expression problem. Okay, number 2 is exactly the same type of problem as on the first page. In fact, it comes from the same book. It's actually the next problem in the book. So I'm going to leave that one for you to do entirely on your own. Let's go on to the next page. So write an equation for a first-order integrated rate law using simulated reactants A and B. And you don't necessarily even have to use B. Identify, explain each of the variables. So you could write a number of them. So there's not just one way to write it. So let me show you one way you could do it. It could be rate. Boom. That's a first order rate law. There's an exponent of 1 there. So that means the order of this reaction is first order. You could also do this one. Watch this. These are just alternatives. Boom, you add the exponents, you still get 1. So that would be a first order reaction as well. Let me show you one other. You could actually do this. Possibilities are endless. Wow, can you have a -1 exponent? Yeah, if the concentration doubled, think about this. If the concentration doubled, and by doing that the rate got cut in half, then you would have a 2 to the x equals 1/2. What would x be? It would be -1. That doesn't all happen very often in chemistry, but it can definitely happen. It definitely happens, and it could happen. So you double the concentration, and for some reason that causes the reaction to slow down. That can happen. So you can have exponents of -1. So 2 minus 1 is 1, so that's all three of these are first order. Okay? All right. I'm going to correct this problem though. I don't want it to say integrated rate. I want to just say a rate law. This was not an integrated rate law. That word shouldn't have been there. I didn't mean it to be there. Okay, so, and I'll correct that on the assignment. If you're there though, if you're already here and you've done the assignment, then that's how you do that. Okay, what is the difference between a standard rate law example, rate equals KA, that's kind of one we showed up here, and the first order integrated rate law? Okay. So I'm going to leave that one for you to answer. You can use the speedometer example and the trip from San Diego to Los Angeles example. One of them is the rate at a specific moment in time. One of them is the time difference between a beginning rate or beginning concentration and an ending concentration. Okay, so go ahead and read that slide, and then put that in your own words. That's key, that you can put this in your own words. I ask you to do that actually in number 5, is do the analogy. So do the analogy here with the car and the speedometer and the trip to Los Angeles from San Diego, and just write the explanation for this for a reaction up there, okay? So don't use the analogy up here, use it down there. All right, let's keep going. Draw 2 sketches. Sketch the graph of A versus T for a first order reaction. Sketch the graph of natural log of A versus T for a first order, it says equation, it should be reaction. It could be equation, it actually is. What is the advantage of the second sketch, and what does the slope of the second sketch represent? That's all in the video. I want you to watch the video carefully, even several times. Okay, it's not entertaining, but it's got the stuff you need to know for this and for this test. Okay, so I'm going to leave number 6 for you to do. It's straight out of the video. All right, let's keep going. Okay, on the next page, it says this problem is directly from the video. It is number for number from the video. So what I want you to try to do is see if you can remember how to work it, answer these 2 questions. And then the second thing is, if you can't, go back and watch the video. So that is in the video that's integrated rate law video for day 52, and just go back and watch it again and answer this. All right. Okay, so you should be able to determine whether something is 0 first or second order reaction based on the graph. And the question you're asking is, what makes the graph a straight line? If you plot the concentration of A against time, if you plot the concentration of natural log of A against time, or if you plot the concentration of 1 over the concentration, you plot 1 over the concentration of A versus time. So you just do those one at a time, and you say, is that a straight line? No. Go on to the next one. Is that a straight line? So I give you 3 of these problems. Okay, they might all be first order, they might all be second order, they might be 1 of each, they might be 2 of one and 1 of the. Okay, anyway, so go ahead and do that. So the first thing you're going to do is, now how can you tell something's a straight line without plotting? By the way, you'll notice that I give you some graph paper on the next 2 pages if you want to actually plot. But let me show you how you could tell. You wouldn't have a chance or time to do that on the AP exam. So how do you tell something's a straight line? Well, first of all, these are increasing in linear fashion. 1, 2, 3, 4. The difference between these two is 1, the difference between these two is 1, and the difference between these two is 1. That's a linear progression. Okay, so what you ask yourself is the difference between these two the same as the difference between these two, which is the same as the difference between those two. If the answer is yes, so what you could do is just subtract these two and write it kind of right in the middle right there on that line. If they do have the same differences between them, then that means that this would be a straight line. And yes, time against concentration of A would be a straight line. So that means that time versus concentration of A is a straight line with a negative slope. Then the reaction is 0th order. That means that would be a 0th order. If you found that these don't give you a straight line, now you got to get out your calculator and just write down what is the natural log of A. So what is the natural log of this? Write it there. What is the natural log of 3.32? Write it there. What's the natural log of this? What's natural? Then take the differences. Okay, it doesn't matter whether they're positive, whether it's a positive number or negative number. Just subtract this minus this, this minus this, this. You get the same differences for all three of those subtractions. If the answer is yes, then that means, then it means the natural log of A is a straight line. And time, that would mean that time versus natural log of A is a straight line with a negative slope. Then the reaction is first order, so you'd know it's first order. If that didn't give you a straight line, you got to go to the third one. 1 over this number right here. So 1 over 4.95, 1 over 3.32, 1 over 2.23. And it's possible that, by the way, that the reaction is none of these. It can be. It doesn't have to be one of those. But anyway, you plot the reciprocal of each of these right there, and you check. You do the same thing with the differences and see if you get a straight line. And if you do, then that means second order. Time versus 1 over A is a straight line with a positive slope. Then the reaction is second order. And again, it is possible that none of these would produce a straight line, and it wouldn't be any of those. So I gave you 3 of these problems. There's A, and there's B and C. So you can just go ahead and write the order of the reaction right up above when you figure it out, okay? I kind of gave you a little tip here that that's a 0th order. If that's a straight line, that's a first order. If that's a straight line, and that's a second order if that's a straight line. Okay, so again, plot this first. If it's not a straight line, then move on. If it is, you're done. If it isn't, though, you move on to the next one. If that's a straight line, you're done. If it isn't, then you have to move on to the third one and plot that. You don't necessarily have to do these in this order, but this makes sense to do this one first. And we do the first order second, the next, and then we'll do the second order last. All right? So go ahead and do that for all 3 of these. You really don't need the graph paper. I'd advise you not to use it. I thought about that after I'd already put it in the assignment. So you shouldn't have to plot these. You should just be able to take the differences, and if they're the same differences, that's a straight line. Okay, let's go on. Okay, this next problem is really just a plug and chug problem. I'm telling you that it's a first order reaction, and a first order reaction is defined by this, that a straight line will be given by if the natural log of A equals, it's a negative slope. You can see that by the negative sign. A first order reaction is a negative straight line, negative slope straight line. Okay, there's a number there. I want you to tell me what that number is, times the time. And then you have a constant here. So remember that this is in the form of y equals mx plus b. So this is the y-intercept. This is the independent variable that in algebra class would have been an x. It's time. In physics class, it's oftentimes time. And in chemistry too. And then this is, what is that? So I want you to tell me what that is. Okay. And it is the slope, yes, but what does the slope represent is what I'm asking. And then this number. And then, so the next question, I just ask you, what is the rate constant? You should be able to tell by looking at that. And then I just ask you to plug and chug 3 problems there. So I give you an initial concentration up here of 0.3. That's going to go in there. And then you just do this 3 times. You may have to go to the back of the page, or I think you can probably squeeze it in over there. And then just plug in each of these for t. Okay, so it's just a plug and chug problem. It's not meant to be hard. Okay, the next one is second order. Okay, I'll do one of these for you. What the heck? Okay, I'm not going to tell you the answer to this. If you don't know the answer to this first one, then I want you to go back and watch the video again. That's straight out of the video, and it's an important point in the video. So all I'm doing here for this one, I'm going to do the 2.4, because there's a little twist at the end that might trip you up. I'm going to do ln A equals this. Times the time. The first one, I'm going to do the 2.4 for you here. Plus the natural log, I'm running out of space here, of this, 0.3. Okay, I trust you can read that. That's natural log, that's the concentration, 0.3. Natural log, okay? So we can go ahead and compute that on your calculator. Again, you need a calculator with an ln on it. Right there I have an ln button. Again, if you need one of these calculators, come see me. Begging you guys to do that. And it's 0.3, natural log of 0.3, and that's going to give us negative 1.2. I'll just leave it at that. Okay, and now it's going to be negative 0.217 times 2.4 right there. So I'm just going to go ahead and do that. Negative 2.17 times the time, which is 2.4 seconds. And then it's going to be minus 1.2, and that gives us this. And I'll just call it, I'm going to leave it at 6.4. Okay? Negative 6.4. Okay, so that's your answer, right? Wrong. You don't want to know the ln of A. You want to know what A is. You want to know what the concentration is. Okay, ln is just a tool we use to get to it. So what do you do now? How do you get that A out of the ln? It's stuck inside of that ln. And that's what we talked about earlier, all the way back to lesson 2, is you use an inverse. So it's going to be E raised to the ln A. And then anything you do to one side, you do to the other. So it's E raised to the negative 6.4. Something doesn't look right about that calculation. Let me do that. It's not. It's 1.72. Okay, so this is 1.72. So it's negative, I'm not sure what I punched, it went wrong. It's negative 1.72. So I hope you got that and didn't go crazy. So let me do it again. Negative 2, excuse me, that's what I probably did. Negative 0.217 times, in fact, I'm almost sure that's what I did. 2.4 minus 1.2. And yes, that's what you should have. So that's what you should have up here in this exponent. Again, one good habit is always try to learn to check your work as you go along. Not just wait till the very end, because you can do a whole page of calculations and realize you made a mistake up at the top and you got to throw it away. Okay, so what does this do? These two are inverses of each other, so what we end up with is simply the concentration of A. That's what we want to know. And E raised to that power, again, what you have to do on this calculator, get it in focus here for you, is the E to the X is right above ln, so you have to push second ln, and then you put in the number. In this case, it's negative 1.72, close the parenthesis, and hit that, and you get 0.179. We'll go with that. And what are the units of measure? For concentration, it's always molar, moles per liter. Let's get that in focus for you. And that's your final answer. So you're going to do the next two. Now what you should notice is something is that concentration should be doing what? Okay, reactant. It's a reactant concentration. What do reactant concentrations do during a reaction? They decrease. So your next two numbers should give you a lower number than that. The next number, the 3.8, should. And after even further time in the future, 5.2, it should go down even lower, okay? All right, there you go. Okay, so I did one for you. Again, you can do these on the back. Again, you answered this question, what is the rate constant for this reaction? And then do that. Okay, next one is second order. I'll do same thing it's asking, what is the rate constant for that reaction? Okay, I'll go ahead and work 4.0 for you here. And we have an initial concentration of 0.2 right there. So that's what's going to go in for A0. A0 is an old-fashioned term. I know it's not, you don't hear it much anymore. It's not. N-A-U-G-H-T, something like that. It basically means nothing. So it's an old school term. Okay, and it's 1 over 0.2. Okay, so now it's just math, and, well, except I should have put my time in there. And I leave myself any space. It's 4 seconds. I'm going to do the first one for you here. So it's times 4. And then I'll put the plus sign right there. Okay? All right, so here we go. Okay, and 1 over 0.2 is 5. It's the reciprocal of 0.2 is 5. Okay, so what I get for this is all right, equals well, it equals 1 over A. I should have actually, I goofed on that. It's 6.66 is the answer to all that. So that equals 1 over A. As I say, check your work as you go along. Okay, so 6.66 is all of this stuff equals this. I just switch sides, doesn't matter. So remember, again, we're not interested in 1 over A, we're interested in A, so you simply take the reciprocal of that, and that will give you, I'll write it on the correct side this time, 0.15. And again, as you go to 6 seconds, again, it's a reactant, it's going to be decreasing. So 6 seconds should give you a smaller number than that. 8 seconds should give you a smaller number than that. All right? Okay, not so bad. Let's keep rolling here. All right. Okay, describe what happens to the rate of a reaction when the concentration of a reactant of the following orders is doubled. So if you double the concentration of a reactant for a 0th order, how does that affect the rate? If you double the concentration of a 1st order reactant, how does that affect the rate? If you double the concentration of a 2nd order reactant, how does that affect the rate? That's in the video. I've talked about it several times. And you want to know those relationships, okay? So go back and watch the video if you don't know the answer to that off the top of your head, okay? All right, so I'm going to leave that one for you to do. That is out of the video. Okay, and we're going to finish up with a half-life problem. Kind of ignore the numbers. The numbering's irregular in this assignment because I changed problems around. Don't worry about the numbers. Just, just the problem is fine, whether the numbers are sequenced or not. Don't worry. So what is the half-life formula for a 1st order reaction? So the way you write that is T subscript 1/2. That means half-life. And that's going to equal a fixed constant number, 0.693 over K, over the rate constant. Does this apply to a 0 or 2nd order equation? No. This is for 1st order. For 2nd order, the T half-life. It's 1 over K times the initial concentration. Okay? All right, so it's a different equation. So what is the half-life of a, and I corrected this in the assignment, it should be of a 1st order. I'm just interested in 1st order here. reaction with K equals that? Well, we just plug the number in. So that'll be and this is this. Okay. And we're not going to worry about the units of measure there. So remember your scientific notation principles here. It's going to be 0.693 divided by 2.1, okay, is going to give us 0.33. That's just for the coefficients in this number. And you have 10 to the minus 4 on the bottom. That means you can bring that up to the top and make it 10 to the positive 4. That's the way exponents work, okay? So that's 10 to the positive 4. And if you slide the decimal over one place, you're to 3.3. You made the coefficient bigger by going from there to there, so you make this smaller. And that's equal to 3,300 if you want to write it that way, okay? So what that means is, assuming we're talking about seconds here, I didn't state units of measure, wasn't very good about that. That means that if you started with 100 molar of a solution, and it was going to, or of any substance, doesn't have to be molar, it's some substance that's going to decay. Then it'll be down to 50, it'll have decayed by half in 3,300 seconds. Then it'll be down to 25 in another 3,300 seconds. All right? And that's how half-lives work. Okay. Okay, and the final question is, what is the value of K for a reaction? Again, it should again be first order. That means you can use this formula right here. Okay, so it's saying the half-life is 2,500 seconds. And it's asking for what the rate constant is, so we multiply both sides by K. Cancel, cancel. Then we divide both sides by 2,500. Okay, and cancel, cancel. So K is going to equal get 2.77 times 10 to the negative 4. Okay, I'm not going to worry about the units of measure here, and I'm off screen also, so there you go. That's what I got from that calculation. It's just to plug in the numbers problem, okay? All right, that's it. I might give you a couple more, and I want to cover a couple other points. That'll be at a later time. Okay, that's it. That takes care of day 52. Day 53 is a lot. Get this thing done and spend some time this weekend with day 53. I'll talk to you about it in class, okay? All right, so we'll see you on that lesson.